Hello everyone, welcome back to the NPTEL course on materials informatics. So, we will be continuing on from our previous lecture where we discussed logistic regression followed by softmax regression, then k nearest neighbors, and then we started discussing on support vector machines, right. So, let us get started with today's lecture. So, just as a recap of where we stopped last time, so we started looking at support vector machines and these are very powerful tools that can do both regression and classification as well. But these models, the support vector machine models, can be quite sensitive to feature scaling. So, remember that support vector machine always tries to put in the largest street between discrete sets of data points. So, here you have purple points here and you have blue points here, and if you used unscaled features and let us say this is the distribution of points, then the largest street that the support vector machine can put in is indicated by the dashed lines here, right. Whereas if we were actually if we manage to scale the features and separate out the data points as so, you see that the street is much wider. So, in general models with wider streets are more robust, so they are less sensitive to outliers compared to models with narrower streets, right. So, it is very important in support vector machines to use standardized features as much as possible. The other important thing to note in support vector machines is this hyperparameter C. This is used for regularizing your support vector machine models, and it works similarly to the alpha parameter in the case of linear regression, just that the C is inversely proportional to alpha, right. So, when we have low values of C, we typically have low variance or high bias. So, basically the model is highly regularized, and if we have larger values of C, then the model has higher variance. So, it has higher tendency to overfit or it has lower regularization, right. So, this is basically a sub collection of data points. So, you have blue data points corresponding to versicolor here and green data points corresponding to virginica here, both belong to the iris flower category. And if you use high regularization, you see that the model tries to fit in a wider street, as large a street as possible, but then the model has a lot of outliers, right. So, a lot of points within the street which are not getting classified correctly, right. So, this is an example of a low variance model, right. But if you now increase the variance of the model, then the model minimizes the number of outliers and it also narrows the street, and it is actually fitting between the green data points and the blue data points, right. So, C hyperparameter is a fairly important hyperparameter that can be used to regularize our support vector machine models, and the way to include C is we first import a support vector classification model, right. So, linear SVC stands for linear support vector classification, and linear models sort of work fairly well for linearly separable data sets, right. So, from scikit-learn as support vector machine module, we import this linear SVC package, and then when you create an instance of the linear support vector classification class, you also feed in the C parameter, the hyperparameter here, right. And then fitting the model is fairly straightforward, works like any other scikit-learn model with the fit function. Make sure that you put in scaled features here alongside the target values here. So, that is how you implement a simple support vector classification model that works well for linearly separable data sets. So, that is on classification. So, how does support vector machine do regression, right. So, it sort of works in a fairly similar way, the only difference being that in support vector machine regression you try to fit as many points as possible on the street, right, and you thus reduce outliers. So, what you basically try to do is, let us say you have a collection of points here, a collection of blue points here, you do identify points that correspond to the support vector. So, basically that help you identify the street, but the support vectors are identified such that you maximize the number of points on the street itself, right. So, you plot a street and then you try to ensure that as many number of points that you have are on the street as possible. So, if the model is considering a point on the street, then its errors are lower. If the models are off the street, so away from the street, then the errors of the model on those data points are larger, right. There is one more hyperparameter that sort of comes up when you have to do regression along with the support vector machine, and that is the width of the street itself, which is referred to as the epsilon parameter. So epsilon is an additional parameter in that works besides your C hyperparameter. So C still tries to regularize or sort of increase or decrease your variance of your model, but you can also include an additional parameter of epsilon that controls the width of your street, right. So you can sort of think of C as sort of plotting the average of the street, the average line, the dark line here, and the epsilon sort of determining where the dashed lines are present as part of the street, right. So if you have higher epsilon values, the model tries to fit in wider streets. If you have lower epsilon values, the model tries to fit in narrower streets, right. So epsilon is not fully unrelated compared to C, so you can sort of think of it as an additional regularization or a variance hyperparameter that works in addition to C, and it is only relevant for regression problems, right. So how do you implement regression with support vector machines? So once again, if you have a linear data set, linear looking data set or linearly separable data set, then you can always use linear support vector machine models, and the regression model is just linear SVR from the same SVM module here, support vector machine module. And when you initialize the class, you pretty much have to define an epsilon or the width of the street hyperparameter. You can also define an additional C hyperparameter here, and once again you fit using the fit function. Keep in mind that even for regression, scaling of features is fairly important, just like your classification. So make sure that your features are always scaled whenever you use support vector machine models. Alright. So we have now looked at linear classification and linear regression with support vector machine. What if you have highly non-linear data, right? So let's take the example of data that sort of looks like this. So you have green data points that sort of lie in the middle. So this is varying with one feature called x1, right? So let's say this is some numerical feature. So you have green data points here, and then the blue data points are on either side of the green data points, right. So this is not really a linearly separable data set. So for example, if you were to say, okay, x1 equals 0 is my threshold, so everything that is below x1 equals 0 I consider blue, above x1 equals 0 I consider green, then you see that you are making false classifications here and also false classifications here, right. Same thing. So if you were to use x equal to 2 or x equal to minus 2, does not matter, right. If you use a threshold at a constant x value, you would see that you would always make wrong classifications, right. So you either misclassify blue as green or misclassify green as blue here, right. So this is an example of a non-linear data set or a data set that cannot be linearly separated. So what do we do in such cases, right, with support vector machine? There are actually two ways to get out of this. One is that we could add polynomial features and continue to use a linear support vector machine model. The other way is to use the kernel trick and use a more sort of regular support vector machine model. Let us take the case of adding polynomial features. So let us say I take this exact same data set, but instead of taking x1 as my feature, I take x1 square. Right. So basically I take the squares of all of the x1 points, right, alongside all of the x1 points for all of the data points that I have. So 0 square is 0, this is 1, and this would be 2 square, that is 4, this would be 3 square, that is 9, right. So if we were to plot the square of the features, right, so I am plotting x1 and then x2 is basically my x1 square here. I see that the data points now arrange themselves into a nice parabola. But the more interesting thing is that now I can now define a linear sort of cutoff value for my x2 feature, which is basically my x1 square, that sort of separates out all the blue points and green points completely, right. So basically if I say for all values of x1 greater than 7 my points are blue, and less than 7 it is all green, then I see a perfect classification, right. So all my green points are below and all my blue points are above, right. So this is one way of getting around a non-linear data set. So we calculate or add in polynomial features into our data set itself, and we do a linear support vector machine model. And this is very analogous to how we were doing polynomial regression, right. So the simplest way of doing polynomial regression is to add in polynomial features or nonlinear features and do a linear regression, right. So this is the equivalent of that with a linear support vector machine. The other way to do it is what is referred to as the kernel trick, right. So what is the kernel trick? The kernel trick is a mathematical trick, and it is often used to obtain transformed versions of whatever features that you have, right. So let us say you want to go from Cartesian coordinates to spherical coordinates, for example. You typically do some kind of matrix multiplications or rotations, right, of your vectors that you have in your Cartesian coordinate, and once you do those multiplications or rotations, the resultant vector would be in a spherical coordinate, right. So going from Cartesian coordinate to a spherical coordinate can be considered as a kernel operation. So where the kernel is basically your rotational matrix or your transformational matrix that you would have to multiply. So we can define similar kinds of kernel tricks for whatever sets of data points. So whatever sets of vectors that we have, vectors as features, or whatever matrix that we have as features, right. So I will give you an example, right. So let us take the very same data set that we saw in the previous slide. So you see that green data points are accumulated at the center, and then blue data points are sort of far away, right. So what kind of kernel can we use to ensure that the green data points become fully separable compared to the blue data points, right. So we could use a kernel called the radial basis function. So what is a radial basis function or a Gaussian function, right. So so what is this radial basis function or a Gaussian or a simple Gaussian function? So so basically we consider one Gaussian distribution of points centered at this value here at this value of -2, and another Gaussian that is centered at this value of, let us say, +1, right. So basically whatever values we have, whatever x1 values we have for these individual data points, we are going to sort of project them onto these Gaussians and calculate and sort of plot those Gaussian values here. So I am basically plotting x2 values here. So x2 are the projected values of these data points on this Gaussian here, right, and x3 are the projected values of the data points on this Gaussian here, on the x3 Gaussian here. So I am basically trying to plot x2 versus x3. So if you look at one of the green data points here, right, so green has, you know, let us say about 0.6 or so on your x2 Gaussian value, and similar and about 0.25 or so on your x3 Gaussian, right. So that is probably this point here, right. So similarly if I take one of the blue points here, so blue point, this one is almost 0 on the x3, right. So on almost 0 on the x3, and on x2 it's reasonably large, about 0.6 or so. So that would be this point, 0.6, 0.7, so that would be this point here, right. So I am basically projecting my x1 values on the two Gaussians, right, and then plotting the values of the Gaussians themselves for the individual data points. So that is what I am doing here. So I am plotting the values of the x2 Gaussian here versus the x3 Gaussian here, right. So if I do that here, I once again see that all my blue data points get linearly separated out from all my green data points, right. So this makes my classification task fairly easy. So all I have to do is identify this sloped you know, separation line here, threshold value here. So below this threshold all of my data points are blue, and above this threshold all of my data points are green, right. So kernel tricks like this are often very useful. So they basically transform data from one sort of representation, one sort of feature representation to a different feature representation, and they help in the accuracy of models. You can also look or think of kernel tricks as a higher dimensional representation of low dimensional data, right. So for example, the initial data that we had was one dimensional, so it was only varying with x1 as our feature here, but once we use these two Gaussians here, our data now becomes two dimensional. So right, so we have an x2 coordinate here and an x3 coordinate here, so our data becomes two dimensional. So we are basically trying to represent low dimensional data into higher dimensional spaces or quantities here. So that is what the kernel trick does, and kernel trick is very often used for non-linear support vector machine models and also other non-linear models as well. So, whenever you have difficulty in using a certain set of or identifying a certain set of relevant features for any machine learning model, you can always consider using the kernel trick to see if that can give you a better representation, right, or a better model. Okay. So, how do we actually implement this kernel trick with a non-linear support vector machine? Mathematically it can be a little bit complex compared to linear support vector machine models. So, it sort of scales of the order of m to the power of 2 or 3 times n, where m is the number of data points you have and n is the number of features that you have, right. So, the larger the data points, the more heavy the model actually becomes when it comes to training. And the non-linear support vector machine models, or the so called regular support vector machine models, actually uses principles of quadratic programming, whereby they sort of incorporate convex cost functions. So that you can use algorithms like gradient descent or the equivalents of them. But they definitely use principles of quadratic programming, which is a little bit more complicated than the simpler fits that we have seen so far. The regression can also be, so we saw an example of classification in the last 2 slides, but you can also implement similar cases or similar models for regression, can also be done with the kernel trick, and the only difference is that we have to include this additional hyperparameter of epsilon in addition to any other hyperparameters that we may want to tune, right. And the way to sort of implement this in practice is we use the same support vector machine module, but we import this SVC class. So, this is not a linear SVC, so this is just SVC. So, SVC is support vector classifier. If you want to do regression, you would import SVR, so which is the support vector regression. So, to create an instance of support vector classification model, we have to include several hyperparameters here. So, one is what kind of kernel that we want to use. There are already several kernels that are possible. So, if you want to simply add polynomial features, you can use a polynomial kernel. If you want to use Gaussian features as before, or radial basis functions, you can use an RBF or a Gaussian here, right. The degree is specific to this polynomial kernel. So, degree equals 3 indicates that we are going to include polynomials up to the degree of 3, so up to the cubes. This coefficient of 0 is also another hyperparameter. It is particularly relevant for polynomial based support vector classification or regression, and it basically determines the influence of higher degree versus lower degree polynomials. So, in general, if you sort of initialize higher values for this coefficient of 0, it sort of assigns more weightage to higher polynomials. So, in other words, it sort of increases your variance of your model if you have higher values of coefficient, and C is of course your regularization hyperparameter. So, generally lower values of C you have more regularization, higher values you have lower regularization. So, once you create an instance, fitting is fairly straightforward. You used your scaled features and your target variables here, right. Okay. So, that was support vector machine, and support vector machines do represent a very powerful way of creating both regression and classification models. Another classical model that is quite powerful in both regression and classification is the so called decision trees, right. And these are quite powerful models, and the main advantage with the decision trees is that they often require very minimal data preparation. So, you typically do not have to worry about standardizing or normalizing your features or your target values. So, how do decision trees typically work? So, they use if-else decisions. So, they try to come up with if-else decisions. So, if a data point satisfies a certain condition, then it is classified as true or yes, and if it does not satisfy, then it goes through a different box or a different condition, right. So, they use these if-else decisions to separate whatever data you feed in to as many pure bins as possible. So, as many bins where only one type of data actually exists. So, let us take an example here, right. So, let us say I pass in about 150 samples of my iris data set here, out of which 50 have labels of Setosa, 50 have labels of versicolor, and 50 have labels of virginica, right. So I have 150 data points, 50 of sort of each category, right. So let us say I now try to classify based on petal length, right. So my decision tree basically takes in a value saying that if petal length is less than 2.45 then it is assigned as true, if it is greater than 2.45 it's assigned as false. And it turns out that if petal length is less than 2.45 I get about 50 samples, and all of the 50 samples belong to the Setosa class here. So this is basically a pure classification or a pure bin, right. So a decision tree has already using this petal length as a feature, it has already classified completely my Setosa class. Now for all the data points that are not Setosa, so there are about 100 data points here, right. So it has already used petal length here, so it tries to use petal width as the threshold or as the feature, right. So for a threshold value of 1.75 it basically tries to classify whether it is versicolor or virginica. So what this branch of the decision tree, so the whole thing is basically our decision tree here. So what this branch tries to do is it takes a petal width as the feature and then tries to see whether it is less than 1.75. If it is less than 1.75 it is going to assign it as versicolor, if it is greater than 1.75 it is going to assign it as virginica, right. So this is true, this is false here, and it turns out that if you actually do this exercise 54 data points actually end up being identified as versicolor, and about 46 data points are being identified as virginica here, right. But these two bins are not completely pure. We see that out of these 54 only 49 are pure versicolor and 5 are actually virginica. So the using just this petal width of 1.75 is not able to separate out the data into very pure bins, but it is as pure as it can get, right, for the simple decision tree. So for versicolor we have 49 true classifications, 5 false classifications here, and for virginica we have 1 false classification here. So 1 versicolor data point has entered here as a false virginica and 45 true virginica data points, right. So this is a very simple example of a decision tree. So we pass in 150 data points, use petal length as the first feature to classify, right. So some of the data points get classified here as true, this is a pure bin, some get classified as false, and then we once again use a different feature here called petal width, and then we classify it into 2 other bins here, right. So this is an example of a simple decision tree. The first node or the first place where you make a decision is referred to as the root node, or its depth is considered to be 0, right. And then the first sort of branch that you get which where decisions are being made, where you get another feature that is being used to create further classifications, that is referred to as a branch node. If you end up going into a node which does not have any branching following it, it is referred to as a leaf node, right. So we see that the root node here gets split into 1 leaf node and 1 branch node here, and both this leaf node and this branch node have a depth of 1. So root has depth of 0, branch nodes have depth of 1, and then once you do one more classification we get 2 leaf nodes, no more classifications here, so 2 leaf nodes, so you have a depth of 2. So this is a decision tree with a depth of 2 basically, right. So how do decision trees, so when they try to do this classification, right, so what decision trees try to do is to identify these threshold values, and they try to identify the threshold values that sort of minimizes this Gini scores, this GINI Gini scores here. So how are Gini scores defined? So they are defined by this mathematical form here. So it is basically 1 minus the square of the probabilities that you have of misidentifying one data point as another. So I will give an example, right. So let us take the case of the root node here. So we have 150 data points. The initial label that is being assigned to this root node is basically Setosa, right. So out of these 150 data points only 50 of them have the correct classification of Setosa, right, and 100 of them have the wrong classification, right. So 50 and 50 have the wrong classification. So if you actually take in the probability of correct classification, right, so Setosa can be classified correctly only for 1/3 of the data points, so 50 by 150. Same thing with versicolor and virginica. So 1 by 3 and 1 by 3. So we basically get 1 minus 1 by 3 square plus 1 by 3 square plus 1 by 3 square. So there are 3 1 by 3 square terms. So we basically get 1 minus 3 times 1 by 3 square and that is basically 1 by 3. So 1 minus 1 by 3 is basically 0.667, right. So that is how the Gini score is calculated, and the decision tree tries to minimize this Gini score as much as possible, right, as it progresses through its through its depth, right. So as it creates more branches and more leaves, it tries to minimize the Gini score in the case of classification, right. So another example is, let us say you take the you take this bin here, right, this leaf node here. We see that there are only 50 samples here, all 50 samples are correctly classified as Setosa. So this has a so the probability of classification of Setosa is 1, probability of classification of versicolor is 0 and virginica is also 0. So the Gini score is actually 0 here, it is 1 minus 1 which is 0 here, right. So we want to minimize the Gini scores as much as possible. So you can sort of think of Gini scores as impurity scores, right. So the decision trees tries to minimize the impurities as much as possible. Another performance metric that can be used instead of the Gini score is basically a cross entropy, is to use entropy as an alternative, and here and this entropy cost function is very similar to the cost function that we saw for logistic regression and for softmax regression as well. So therein you try to put in the entropy term and you try to minimize the entropy term as much as possible, right. So this is how the decision trees sort of work. So they try to use if else decisions to separate data into as many pure bins as possible. You can also think of it in an inverse way, where they try to, for any given data point, they try to predict the probability that a given data point is in a specific bin, right. So let us say you pass in 150 data points, a decision tree tries to predict the probability that 50 of them are in Setosa, 50 of them are in versicolor and 50 of them are in virginica. So it tries to predict that probability as well. So this is another way of interpreting how decision trees work. Okay. So how do decision trees actually end up doing this classification, right. So decision trees actually do not use the gradient descent algorithm that we had seen before. They use a specific algorithm called CART, which stands for classification and regression tree, right. So basically the way CART algorithm works is it tries to separate data sets into as pure bins as possible by creating splits that are perpendicular to your feature axis, right. So let us say this is the distribution of data points that you have initially, right. So you have the Setosa data points here, you have the virginica data points here and you have the versicolor data points here, right. So what CART initially tries to do is it sort of sees petal length as a feature and it tries to create a split that is perpendicular. So for a given value of petal length, it tries to create a split which can create one clean bin or one pure bin and one sort of impure bin or an impure branch, right. So for the root node, it basically tries to have this as its decision threshold. So create a perpendicular sort of split along the petal length axis, and this creates a pure bin of Setosa, right. So this is what happens in the first root node, and in the first branch node, what the CART algorithm tries to do is it has already created a split along petal length. The remaining axis that it has is along petal width, right. So it now tries to create a perpendicular split along the petal width axis or a given value of petal width, right. So data points above this are one type and data points below this are of another type, right. If you were to create more splits, right, so after this petal width split, if you want to create decision trees of more depth, right, then the next split that it will try to create will be once again along petal length or in a higher dimensional space. So let us say you introduce newer features, it will try to create splits along that are perpendicular to those features, right. So or for a given value of those features, right. So this is how the CART algorithm works. So every time you feed it in a set of features, it tries to identify a threshold value for a given feature or create splits in the data set that are perpendicular to that feature axis, right. So the CART algorithm is actually quite powerful. So at any given instance it can either take a single feature such as petal length, petal width here, so it takes one feature at a time, but it can also take multiple features in one go to make decisions. And the way the algorithm sort of scales with number of data points and the number of features is n cross m. So n is the number of features and m is the number of data points you have. So it's sort of it scales a little bit better compared to your regular support vector machine models. And the way to sort of implement decision tree classification is using the tree module under scikit-learn package. You would see a decision tree classifier class, you can import that, you can create an instance and then you can do a fit. So just like you can do classification with decision trees, you can also do a regression, right. And what does the algorithm, what does the CART algorithm try to do in regression, right. So in the case of classification you are trying to minimize your Gini scores or your impurity scores. In the case of regression you try to minimize your mean squared errors, right. So you try to create splits within your data set or put data points into bins which minimize your mean squared errors as much as possible, right. So if you take the example of this collection of data points here, so this is a roughly sort of quadratic looking collection of data points, quadratic along your x1, so y is probably a roughly quadratic function of your x1, right. So what does the decision tree do here? So in the root node, so when your depth is equal to 0, maybe it tries to create a split along this axis, right. So it will have two specific mean squared errors, right, and those mean squared errors will be large. So it basically tries to predict one value for a set of data points that are here and one value for a set of data points that are here, right. Obviously those mean squared errors would be large, so it now tries to create one more split of your data set. So it creates one split here, one split here. So the data points now within this range have a singular value, data points within this range have another singular value, and data points above or below this range have a different singular value. So if you end up creating more and more splits of your data, right, you see that you can start reducing your mean squared errors, right. So basically if you split or if you create so many splits of your data set all the way to creating one split per data point, you basically have a perfect model or an overfit model basically, right. But that is what the decision tree will try to do. It will try to minimize the mean squared error for all the data points within a certain bin, right. So it will assign one value per bin and it will try to minimize the mean square errors for all the data points within that bin, right. And as you keep increasing the depth of the decision tree, it will try to create more and more splits of your data set such that it minimizes the mean square errors within your data set, right. So decision trees can be quite useful for regression, but keep in mind that they can overfit quite easily. And the way to implement decision tree regression is once again using the tree module, you import the decision tree regressor class. Okay. So what kind of hyperparameters do you have in decision trees? So it turns out that there are plenty of hyperparameters. The important thing to note is that there are a few hyperparameters which follow this max rule. So which sort of indicate, okay, what is the max depth of your trees? How many branches or leaf nodes should you have? How many levels of branches or leaf nodes should you have? What is the maximum number of features that you should consider, right, when you are making decisions at any given node? How many leaf nodes should you have, right? So you would have a set of maximum features and you will also have a set of minimum features, right. So how many, so for example minimum sample split, right. So this basically indicates what is the minimum number of samples each node should have, right, before it can be split. And same thing, so how many samples should you have per leaf node, what is the weight fraction for each leaf node and so on, right. So you would have a set of maximum features, you would have a set of minimum features. I am not listing all the features here, right. The important thing to note is that if you want to regularize your model more, so if you want to reduce the variance of your model, you should reduce the maximum parameters and increase the minimum parameters, right. So reduce maximum depth, for example, so that reduce the number of splits that you can have in your model, or the number of bins that you can have in your model, and that basically leads to higher regularization. So if you increase the maximum number of features, so increase the depth, for example, that would allow allow the model to split the data into more and more pure bins and hence have higher variance, right. So if you want higher regularization or higher bias in your model, you should reduce maximum parameters and increase the min parameters. Okay. Another important thing that you should keep in mind is that decision trees can often be unstable and can be very sensitive to the presence or absence of outliers, right. So let me give an example, right. So let us say you have a set of data points, so you have circles and triangles here that are plotted along two features x1 and x2, right. So this is a nice distribution of data points along these two features, so your decision tree can create a very nice perpendicular split of your data along your x1 axis, and you know it can classify all your circles and triangles very efficiently, right. Now if I were to consider the same data points but with a rotated set of features, so let us say my x1 is a rotated version of x1 and this x2 is a rotated version of this x2 here, right. Now you see that the decision tree, since it only creates perpendicular splits, right, it now has to create a complicated set of you know if else decisions, right, in order to clearly separate out your circles from your triangles here. So in other words, your decision tree cannot take in you know a sloped version or a slanted line of a decision threshold, right. It only creates perpendicular splits of your data alongside your features. So if you have rotated features, you may need very complicated decision trees in order to do a simple classification task compared to a non-rotated set of features, right. So rotation of features will almost always result in different decision trees themselves for the same classification or the same regression task. So one has to keep in mind. So if you see that your data set requires a very complicated decision tree, you may want to revisit how the features are defined and maybe try out some rotations of those features that could potentially simplify your decision trees. Another important thing to note about decision tree is the influence of outliers, right. So this is the same data set that we saw before, the iris data set, and you see that there is a very you know one specific outlier here of your blue data point in your green region, right. So if you were to remove this data point, so if you were to remove this outlier, the decision tree model will become completely different, right. So instead of creating a split along the petal length, it will actually create two splits along petal widths, right, that can completely separate out your Setosa, your Virginica versicolor data points, right. So just removal of one outlier completely changes your decision tree model, right. So this is also something to keep in mind. So decision trees are very sensitive to outliers and they are very sensitive to rotation of features. Okay. So with that we will summarize you know today's lectures and overall our discussion on classical models. So we looked at our logistic regression and softmax regression as examples of classification models. We looked at k nearest neighbors which can do both regression and classification tasks, and we also looked at support vector machines which tries to you know identify streets that either separate data for classification tasks or include data for regression tasks. We also looked at decision trees which split the data into as many pure bins as possible to reduce impurities in the case of classification tasks or to reduce mean squared errors in the case of regression tasks, right. We also looked at some hyperparameters and a brief overview of the CART algorithm which tries to create perpendicular splits of data along your feature axis, right. So with this we sort of conclude on the sort of classical models. In the next lecture we will go towards more ensemble models, sequential learning and also dimensionality reduction, and the set of slides will also have a set of important functions or classes as a summary. This you can use to take a look for you know starting from linear regression all the way to decision tree regression. This will be a useful summary for you to have. So with that I thank you all for joining today's lecture, and I will see you all in the next one.